Hey, hello, and welcome here. We have now got to the last week, believe it or not. So here is the start of week number 6, and we're at the end, and things are going to go really, really quick now here. So let me just kind of recap where we are and where we're going. Make sure you hear all this. I hope you took my advice over the long weekend, that you did all the other chapters and all the other labs and you got all that stuff done, because now it's kind of just a race to the finish and a lot to do. So if you recall, we were working with optics. We're going to continue with optics. I left the drawings on the board over the weekend and the 4 days, so I want to come back to those. That is the end of chapter 17 here, and so let's wrap up 17 and then let's finish 18, because if I hold up the schedule here, let me find it. Here we go. Here's where we are. We are right here on June 22nd on Monday. And we are really a chapter behind, and that's understandable given the way things are happening this semester. But the goal here is to finish up chapter 18. And so your test will be on 15, 16, 17, and 18. Now, the original syllabus also includes 20. And so let me emphasize, the email I sent you hopefully made that clear. The test is not on chapter 20. So again, your test is on those 4 chapters, 15, 16, 17, and 18. So we're about to finish up our optics. So tomorrow, Tuesday, like all our other test days, so this is our 3rd one, it's the same style. Test number 3, it's on there on Canvas right now, and if you've looked, you'll see that it says locked until 11 o'clock, June 23rd. So that's tomorrow. And so at 11 o'clock tomorrow, hopefully you can just click right there and get started. And the test, the 3rd test, is a little bit smaller than the other tests, because we have a few chapters. We only have these 4 chapters, again, 15, 16, 17, and 18. And so I decided to do 5 multiple choice each, so that came out to only 20. So there's only 20 multiple choice this time instead of 24. But there still is the 10 free response questions. So that the free responses are the same. So it's, like I said, it's shorter, but not that much shorter. It's just 20 multiple choice instead of 24, but still 10 free response questions. And so today we'll have our 2 lectures and our lab, and so we'll do the spectra lab. Tomorrow, though, we will only have the 1 lecture, okay? Because we do 1 lecture and 1 test on a test day, and so we will go into chapter 20 and do chapter 20, and that's where we'll have to finish the semester, a chapter behind what the syllabus had us going through, and then the rest of this, like I said before, you'll see later on in Physics 1, in this case Physics 122, and some of the other stuff 123, but I think you're in a great position to be ready for the next semester, which is Physics 121. So that's really those first 8 chapters that I kept emphasizing to you. So that will be your next semester. I mean, your next semester, and then tomorrow, your next day. And then on Wednesday, let me just hold it up again, Wednesday, there's only one big event on Wednesday, and that's your comprehensive final exam. And so on the 24th, on Wednesday at 11 o'clock, and again, if you go to Canvas right now, do a double check with me. Check there, but I got that all on Canvas, loaded and ready to go. And so it'll unlock at 11 o'clock on Wednesday. And the final exam is going to be a little longer. In fact, the final exam counts the equivalent of a test and a half. And it's more than a regular test. And not only is it comprehensive, so there'll be questions all the way from way back in chapter 1 and 2. Remember, 1 is converting units, and then 2 are things like what's the difference between speed, velocity, and acceleration. And so there'll be questions all the way up to chapter 20, which is on static electricity. So kind of our little intro to electricity is about as far as we'll get this summer. And that test starts again at 11 o'clock. Now, the good news on that one is that's all we do that day. There are no lectures, there are no labs, there's just the final exam. And so while you guys sit down to take that final exam, I'll sit in front of my computer from 11, in this case 11 to 2. And so you'll have the whole time frame. If we were face to face, that's what the time frame would be. 11 to 2, and I would just sit up front here and you would take the test. Most of you, it won't take you the whole time. It is a little longer. It's 36 multiple choice questions and only one more free response. So there's 11 free response. So again, I'll say it again, 36 multiple choice and 11 free responses. And so that's kind of the layout. I should also say tomorrow, the quote-unquote lab, I'm going to do the same thing on test 3 that I initially did with test 1 and test 2. I think that worked really well. I will make a solution. So right after you guys get done taking the test tomorrow, you guys will be done 11:45. And so let me emphasize, remember, Canvas locks at 11:45. It's not human. It doesn't give you any slack. So just remember that. So when 12:30 comes along, your best bet is to think of it as the end of the test. I know that if you're not done at 12:30, you're going to want to keep going. But luckily, this test is a little smaller. Let me encourage you, at 12:30, do your scanning and your uploading because you don't want to miss the 12:45 cutoff. All right, so with that said, once all that kind of clears up, so maybe about 12:45, maybe 12:50, I'll just say 1 o'clock, I'll sit down and I will make the solutions to it. And so I want to get that out there as quickly as possible. I don't know how, by the time I make it and I transfer it from my phone to my computer and then from my computer up to YouTube, and YouTube processes it and I send out a link, it's maybe 3 o'clock. So give me a couple of hours to actually take the test myself and then transfer it all. So after about 3 o'clock, look for that. You probably do want to take a look at it before the final exam, so sometime after 3 o'clock on Tuesday, but obviously before 11 o'clock on Wednesday morning. Go ahead and take a look at the solutions, and then you'll, I think, be ready for the final exam. And then, believe it or not, it's hard to believe, but I'm talking about a final exam, and you guys will take the final exam and be done. And then I can post grades. Now, usually I post grades, and this whole online thing is new to me as well as you. My normal way of doing things is to post them on a Google Doc, but with Canvas, I should be able to do that. So let me see if I can figure out how to do it on Canvas. I know it's totaling up the points, but it's not weighing them right. Because you know, I've got 100 points for a lab and 100 points for the test on Canvas, but that's not a fair comparison because the one lab is only about 1% of your grade, whereas one test is 16 2/3% of your grade. So it doesn't seem to compare there. So I got to figure out how to make Canvas do what you would call a weighted average and then display a grade. If I can get it to do that, great. If I can't figure it out, then maybe I'll just do a Google Sheet. If nothing else, I know for sure when I put it into Pipeline, then you can see your grade. But I'm used to posting them on a Google Sheet and not Canvas first, and then students usually see them first, and then later on, about a day later, I'll put it into the Pipeline system. So I'm just kind of thinking out loud, but let me figure that out and get back to you. Anyways, we better get started here because I want to make sure we finish chapter 11 here, and we're almost done with, 18. We're almost done with 17 here. So let me jump back here into then this discussion we were having, and just kind of remind you, I will turn on the laser again, but if you take a reflecting surface, a mirror that is curved inward, so we call it concave, there's this magical point. You might remember all this drawing then. We called this then the focal point, and the distance is the focal length, and the focal length is half the radius of curvature. And so in this contraption up here, just looking at the curvature, if I were to draw back, it kind of looks like the center of curvature. Maybe I'll put a little C right there. And then this is the F, this is the focal length. And so roughly that looks like the focal length is half the radius of curvature. And that's what I was trying to show in this picture. Let me not repeat it. You can always go back to that video, repeat it if you want. But that's what we did last Wednesday. In fact, we also then drew these rays. And let me get a couple of my colors here. How about the blue and the green? But we drew this, and I left you at a spot that I said is pretty hard unless I help you. And so that's the good news I want to say here, because your author just says, hey, put the object out here, and it will form an image right here, and then the question is, how big is the image, and what is the location of the image? And there's some fun geometry here, and some pretty tough geometry, although once you get the hang of it, you'll see this. And so let's do the same geometry 4 times, and you'll see how this works. And we'll actually do the same kind of thing in Chapter 18. So the good news here is, as you sit down to do the homework, and for that matter, when you get ready to do the exam, you can view these equations. You can write these equations down because, you know, being online, it's kind of open book and open note, so you can look at these. You don't have to work them out yourself. Even in a face-to-face setting, I put it on the board so the students don't have to work it out themselves. But I do feel like I need to go through it in class because, as I was saying, your author doesn't do it in class. Your author just says, it's just some geometry, the students can do it. And I have found that that's asking maybe a little too much. So here's what I'm going to do is let's go through the geometry. So if you remember me drawing this, here's the image. You can just see, hopefully, in the picture that the image is upside down. You can also see that it is smaller than the object, and you'll also see that in the mathematics. And the mathematics kind of begins like this. If I take a blue, well, yeah, this is the one I want. I shouldn't have drawn the blue up here. But if I draw that blue, you will hopefully see that as I trace those rays, I've got 2 blue triangles. And I want to convince you that those 2 blue triangles are similar triangles. That's really the key to the geometry. And the real key here is to say from our geometry class that when you have 2 lines that cross, those 2 angles are equal. Those are called vertical angles. And so our vertical angles are equal. Now, given, and I didn't do a good job of drawing all the way back to the object, so let me go all the way back to the object. But this would be a right angle, and this would be a right angle. And then, since we know that all 3 angles of a triangle add up to 180 degrees, if you have 2 of them that match, the third one must match. So this is saying all 3 angles match. This is called similar triangles. In other words, they have the same shape. And they don't necessarily have the same length. In fact, you could even just see in my drawing that they don't look the same length. So these are not congruent triangles. In fact, maybe as we start today, I should just kind of review. Maybe I'll come back here to the far board and just remind you that we did a little bit of geometry, the simplest geometry for the flat mirror. We said for a flat mirror, the object distance is the same as the image distance, and the object height is the same as the image height. And so that was the congruent triangles, and because of that, the lengths were the same. But what I have over here then are triangles that are similar but not congruent. And if you look closely then at this blue triangle, especially this one here, you'll see that this right here is the same as the height of the image, and that this length right here is the focal length. And this whole length is the distance where the object is. So that means this length right here is then the object length minus the focal. And so here's where my similar triangles are going to come into play. I'm going to say the height of the image to the height of the object. So this part of the triangle compared to that triangle would be the same as this part, which is the focal length, over this part, which is the object distance minus the focal length. So here's how the math would work. You might get a question like this that says, how big or what is the size of the image? And when it says what is the size of the image, probably in there they will say you have a concave mirror, and they will probably say you have a concave mirror with the radius of curvature of, and now my point is they would give you this number. So if they gave you this number r, then you know the focal length. And so coming over to this equation, usually what would be given in a problem would be something like this. The focal length, I will say, is given. Now maybe not directly given, because they would give you the radius of curvature. Okay, so they give you the radius of curvature, and from that you can get the focal length. And then they say they put the object in front of the mirror a certain distance, so they give you the object distance, and they tell you the height of the object. The object is, say 4 centimeters high. And so my point is, in this equation, they would give you everything but the height of the image. And so therefore you could calculate the height of the image. And so that's the key here. And if you look closely at this, this number, at least with it sitting over here outside of the center of curvature, because remember the center of curvature is twice the focal length. That means when you subtract this, this is always less than 1, so that would always be less than 1. And so that's what I was saying. This would create an image that is smaller than the object. Now, let me do another set of similar triangles. Maybe I'll do that in the green. But if I make a triangle out of the image that extends back into the mirror, and so it's kind of what I just did. Here I did a triangle that had the object that extended back into the mirror. Now I'm doing a triangle that has the image and also extends back into the mirror. But it's the same kind of logic. These would be vertical angles, these would be right angles, and so these would be the same. And so these two green triangles are also a pair of similar triangles. And if you look at the height of this green one in the mirror, this is the height of the object. And so if you take this green triangle, which you could say is the height of the image here, because that is the image, compared to this side, which is the height of the object, it would be the same as this distance. Now maybe I should clarify. This right here would be the distance of the image. So this length right here would be the image distance minus the focal length, because that right here is the focal length. All right, so height of the image is to the height of the object as image distance minus focal length is to the focal length. So assuming we had already done the calculation in this step, and we have now the height of the image, we now, knowing the F, knowing the height of the object, and now knowing the height of the image from this calculation, we have just the one unknown: where is the location of the image? And so maybe I should put a box around this, because this is how you would handle that question. Where is the image? How big is the image? Although maybe I should say it the other way around, because the first one you want to calculate is how big is the image, so you know this. So you can use it down here to get where is the image. Now, let me take all my markers and move down here, because if our drawing were to change, then these equations wouldn't be valid. And this is where I guess you got to pay a little closer attention to your optics, and it becomes a little bit harder, because I would say that as long as my object is further away than the center of curvature, whatever I would draw would look just like this. And so I would say this equation is valid, but it is only valid if, in fact, maybe not, I should write it on the board. I should say it's only valid if, and so here's this if, the object distance is greater than twice the focal length, which is equal to the radius. In other words, as long as our object is beyond this center of curvature here, then we would have that same drawing. And so I'm going to go ahead and come over here and do another drawing and ask this question. What would happen if? And the if would be, what if the object now is closer than the center of curvature? And what you'll see here in a second is when I say closer, I'm going to say, well, closer but not too close. Because if we get in front of the focal length, something even different happens. So let me draw a picture where the object is between the focal length and the center of curvature. So it would look something like this. And I want to erase the simple one. That equation, what I just erased, I call the simple one because it's for the flat mirror. And the flat mirrors are the easy ones. But now that you saw me do the rays and the geometry, maybe now it won't be so hard when I do it a second time. I'll even do it a third time. So hopefully by the time I do it 3 times, you're getting the hang of this. So let me put these 2 magical points. There's the focal point. There's the center of curvature here. And let me go ahead and put my object right here. And let's draw those 2 rays. Now last time I did it in red, so I will do it in red again. And so the first ray to draw, I think, is the easy one. The ray hits the mirror, bounces off, and goes through the focal point. That was our whole discussion about this shape and getting a focal point. And the second one was the little harder one, but if you remember, this was our argument that the light does the same thing in reverse. And so a ray that would go through the focal point, when it hits the mirror, would then go parallel. And then if you also remember our discussion about somebody standing over here, and as these rays were coming to this person's view, and so in this case you might say this ray would go to my left eye and this ray would go to my right eye, and your brain would trace them back from where they're coming from, and your brain would think they're coming from there. That's why we call this then an image. And we say, okay, there's where your brain thinks it's coming from. Now I just noticed that over here I didn't actually put the word image over here, so let me walk back over here and put image. Because I do want to say a little bit about these images, but I do hope you see that this drawing in some way looks a little different. Now it's just a little different, not too much different than this one. In fact, if you look closely at this, I would say the one I've just drawn is exactly this one in reverse. Here's what I mean by that. This had an object outside of the center of curvature, and it made an image between the focal length and the center of curvature. This did exactly the reverse of that. This one started with an object that is between the focal length and the center of curvature, and the rays come out and make an image that is beyond here. And so when I do a set of similar triangles, I'm hoping you won't be too surprised that it actually does come out to be the same equation. The difference, though, being the result of the image. The image here is bigger than the object. I like to say this way, that these two are really kind of the same. The one that is between the center of curvature and the focal length is always smaller than the one out here. So if your object starts out here, then your image is going to be here and smaller. But if your object starts in here, then your image is going to be outside and bigger. And they're always inverted. So this mirror is kind of what I call the fun mirror, because notice that this mirror made things upside down. In this case, it made it upside down and smaller. And back here, what we're trying to draw now, it's making it upside down and bigger. But why don't I draw the same set of similar triangles? If you remember over here, I drew the one in blue that had the object and then its image projected into the mirror. So let me do that same thing. So if we call this then the height of the object, and again we call this whole thing the object distance. Just like over here, if we call this the height of the image, and we call this whole length the distance of the image. And if we draw a triangle here, and this one's curved, so this is kind of an approximation of a triangle. So it's not perfect, but you can see they're not curved by too much. I mean, you can see in here that there is some curvature, but it's pretty close to being straight. So if you let me just kind of roughly say that's a straight line, and so our equations I'm about to get are about roughly true, you will hopefully notice, like we did over there, this right here is the height of the image, and this distance, of course, is the focal length. That makes this distance right here the distance of the object minus the focal length. And this set of blue similar triangles is actually the same thing over there, where I would have the height of the image is to the height of the object as the focal length, so this distance, is to this distance, which would be object distance minus focal length. And so if I come back over here, it's really the same equation. So here's some good news for you. Even though you might say this is a different scenario, it's not a different set of equations. The equation is still the same. If you were to come over here and, of course, be given something like, what is the distance of the object and the height of the object and the radius of the mirror, which would give you this focal length, you would know everything in this equation but right there. And so you could find out the first half of that question. What is the height of the image? And the green one comes out to be exactly the same. And so let me draw a set of green similar triangles. And then point out a couple things, like this size of this green one here is actually the same as the height of the object, so I'll put that there. And then this part of this green one from here out to here would actually be this whole distance, the image distance, minus this focal length. So this is image distance minus focal length. So if we then do something like this, we say height of the image, so height of the image, so this side is to this side, height of the object, would be the same as this distance, which is distance of image minus the focal length, as to this one, which is the focal length. And again, if we come back over to here, you'll see that that's exactly the same equation we had over here. So here's some good news for you. Even though there's kind of a different physical result, the equation is still the same. That is, this situation where the object is between here results in a bigger upside down image, but the way you would calculate it would be the same way. And now you could even see that if this number here is less than twice of f, this ratio is greater than 1, and that's why it is bigger than 1. It's bigger here. And so you can see in the math that it's always going to give you a number that's bigger. And so I'll put a box around this also, but maybe I can then summarize the two together and say, well, this would be true as long as the object distance is greater than the focal length. Because I just proved it was true between the focal length and the center of curvature, but that over here, greater than the center of curvature, we also had that same set of equations. And so maybe I could say, well, don't even worry about that set of equations. Although it's nice to see this picture. It's nice to realize that the image is actually upside down and smaller. Whereas over here, the image is upside down and bigger. And in fact, not just bigger, but further away than the object, if you were saying further away from the mirror. Whereas this one over here, the image is closer to the mirror. So I want to emphasize that there is a difference between these two scenarios, but it's not in the math. The math is the same. And so if you just go ahead and just not even worry about the picture and do a calculation, the calculation will show you when you're done that the height of the image is bigger than the height of the object. And then when you do a calculation for where is the image location, you'll see that the image location is greater than the object's location. That's just the way the math works out. And so it's good to memorize it and see the pictures, but it's also just do the calculation and it falls into play. Now, like I said, this is the fun mirror because there's a third scenario that can come out. And for better or worse, this is a different equation. I wish all three of them came out to be the same equation because it would be a lot easier to teach and probably a lot easier to learn if all three had the same scenario. But this one is a little bit different. And so the third possibility, and of course now you can see it, so the third possibility with this mirror would look something like this. Here's the concave mirror. Here is the focal point. Twice that makes the center of curvature of the mirror. And what would happen if I put an object there? So now the object is closer than the focal length. And you can see in a moment why I did this one last of the three. This is by far the harder one. Let me start with drawing the rays. And so let me grab my red marker here, okay? And I'll draw the easy one first. The easy one is what happens to the ray that goes, I'll call it straight or parallel to the optical axis. And as we did on these other drawings, we would just say, oh, that goes right through the focal point. Sure. But the second one was the little harder one, and even more harder in this one. If I can say more harder, harder in this one. Because watch this one. Remember the second one we drew was the one that went through the focal point first and then hit the mirror. So if we come over to here and we draw the ray that comes from the object through the focal point, it doesn't hit the mirror. So that's not quite the one we want. What we want is the one that's going to hit the mirror. It's coming from the object, and this is kind of the key, but it's coming at the angle as if it went through the focal point. That kind of makes sense? So I'm going to do a dotted line there to say, look, it didn't come from the focal point. It actually came from the object, and it's heading towards the mirror. But I'm picking the one ray that is coming from the object at the appropriate angle. And the appropriate angle is the angle as if it is coming from the focal point. So that's the one that when it hits the mirror here will bounce off and go parallel to the optical axis. So those are your two rays. And like I said, that's looking already a lot different than these other two. And in fact, somebody standing over here would do what? Well, they would say this ray goes into my left eye and this ray goes into my right eye, and their brain would process it, and these two do not actually meet, although they have the appearance of coming from right here. So they have the appearance of coming from somewhere back inside of the mirror. This is like the flat mirror we did. Where is the image? It's actually behind the mirror. I didn't emphasize that. Did you catch that this one, the image would be appearing to be coming in front of the mirror, not behind it, not even on the mirror, but in front of it? In fact, this one, it could be kind of even different in the sense that it is not even close to the mirror. The light is in front of the mirror. It's not behind it. It's not even close to the mirror. It's way in front of it. And so I'll say it again, and I'll show you in a moment. This is the fun mirror. There's some interesting effects you can get from this light. But this one, then, the image appears to be back here. And so maybe I'll put the word here, image, to emphasize, where is it? But this third scenario, I think, is very different than the other ones. Notice that the image is bigger. Notice it is right side up. And notice it's behind the mirror. In fact, to help clarify this, let me give you another important word here. And maybe I'll do this in orange. Over here, this image we call a real image. What we mean by a real image is the light actually bounced off the mirror and was redirected by the reflection off the mirror, converged to this point, and then after it passed through this point is spreading out. So if you were to ask me where is the light coming from, I would trace it back and say it really is coming from here. That's why I want to use the word real image. See, compare that to this scenario, which is also the scenario that we did for the flat mirror. The light never really came from right here. It has the appearance of coming from there, right? See, the light came here, hit the mirror, spread out, and so it has the appearance of coming from this spot. And so that's why we're going to refer to this as a virtual image. And so the real image is an image, and the virtual image is an image. They are both images. They are both places where the light either really comes from because it was redirected, or it appears to come from because it was redirected. But either way, it was redirected from the reflection off the mirror. It's not really where the object is. So we call them images, but we then separate those into different types of images, a real image versus a virtual